So let's start with a little bit of a review from yesterday, just a short one. So we had this definition of a Borel reduction. So the idea was that we had this space for a language L or L prime, we're dealing with two languages. We had this space mod L of all the L structures. And this was a Polish space, and we had this idea of what a Borel map was. And the idea was you're supposed to think of it as just some kind of reasonable construction. And so the settings, we've got two classes, C and D. They're closed under isomorphism, because if you remember these mod Ls, they contain different isomorphic copies of the same structure. So they're not just like isomorphism types, they're differentiating the different presentations. So we've got these two classes of structures, which we really think of as classes of isomorphism types because they're closed under isomorphism. And we say that one is Borel reducible to the other if there's a Borel map that takes structures of the first kind, so A and B, and they turn them into structures of the second kind, 5A and 5B, and they should maintain the isomorphism type. So A is isomorphic to B if and only if 5A is isomorphic to 5B. And the idea was that if C is reducible to D, that means that C is no more complicated than D is. So for example, any invariants that you could apply to D, you could carry them through this and apply them to C. And then we had these classes of structures we looked at that were Borel complete, which meant that every other class reduced to them. So these classes, the isomorphism relation for these classes is as complicated as isomorphism can possibly be on uncountable structures. We had some examples last time. So graphs was the first one, and then all these other classes, partial orders, rings, integral domains, groups, and fields. And something I tried to highlight last time was that in each of these cases, it's not just that we have a Borel reduction, we have something a little bit stronger. It's a very nice kind of Borel reduction. So we talked about these computable by interpretations a little bit, but essentially the idea was that if you map A to B, then you can still recover A from B in a very nice way that A really lives inside of B. So for example, when we showed that when we showed that graphs were Borel complete, we took some arbitrary structure, and we took the elements of those structure, and those became certain vertices in the graph. So the structure really lived inside of the graph in a certain way. And then we had to code in what was happening, which vertices those were and what the relationships between them were. But that was all really coded like inside the graph. You could really find the structure inside of the graph. So in particular, when you have a reduction of this strong kind, you get a bunch of consequences. So the structure and the one you find it in, they're going to have the same automorphism group. You can recover a copy of the original one from the one you produced from it. So you can computably reverse this operation also. And then these two structures, the original structure and the one you produced from it, they really share all the same computable structure theoretic properties. So if you're a computable structure theorist, you have lots of properties that you know. They're going to share all of those. In particular, there's things like computable dimension or degree spectrum. I'll talk about degree spectrum in a second a little bit more. So in some sense, really, the structure and the one you build out of it, they're the same in some kind of very general sense, right? Obviously, if one's a group and the other's not a group, that's a difference. But they have a lot of the same sort of abstract structure theoretic kind of properties. So we called these classes universal or computably universal when it was really computable to go back and forth. So some of these properties here, this top one having the same automorphism group, that's just about being universal, just some Borel map one way, and you can find it in a Borel way. But to share the same computable structure theoretic properties, you really need to be able to go both ways in a computable way. So we compared this to trees and linear orders. So these two classes are Borel complete, but it was a very different kind of argument. So linear orders I kind of went over quickly, but trees we went over in more depth. It was this tree of tuples construction, where you took a tree of all the tuples coming from the structure. And so an element from the structure now showed up in the tree in many different places as part of all the different tuples that it belongs to. And so the structure really didn't belong in the tree. We had to do this back and forth argument to show that this process maintained isomorphism. So these ones, they're not universal in the sense before. There's this Borel reduction, but it's not this strong kind of Borel reduction. In particular, you can say that there's automorphism groups of these structures of trees and of there's automorphism groups of some structures, which are not the automorphism groups of a tree or a linear order. So for a linear order, any linear ordered structure, that's sort of the fact that it's got an order and automorphisms have to maintain the order means that there's certain automorphism groups that can't happen. So for example, you can't have any torsion in the automorphism group. If this element maps to this element, you can't have this element map to this element, right? You can't like have the loop like that. In a tree, you've also got some limits. So for example, if you have an automorphism that takes this element to this element, this element to this element, and this element to this element, so something like an automorphism group of C3, the cyclic group of order 3, then you're going to have some other automorphisms as well, because you're actually going to be able to map these two things to each other, keeping that thing the same. So just the picture there, essentially, you've got some tree, and what you're saying is if you can map this to this, and this to this, and this to this, that means that the subtrees below all those all look the same. So you could say, I just want to fix this one here, and I'm going to swap these two. And that's also going to be an automorphism. So there's sort of some limitations on the automorphism groups of these structures. One general question, which I don't really know what the answer to it is like, how does that connect? What can you say about a class of structures by what kinds of automorphism groups are realized there? So I think Russell has a paper where he talks about differentially closed fields and their automorphism groups a little bit. They also have this property that not everything is the automorphism group of a differentially closed field, and yet you can still do some kind of coding. So I think this idea of like how computable structure theory interacts with automorphism groups, that's sort of a fruitful place to look at things. And then maybe a number of the hardest questions of computable structure theory, you can really think of them as saying, let's look at these classes of structures which are that are not universal, but they are Borel complete. So somehow they have a lot of complicated structure taking place in them, but they're not so complicated that they do anything that any structure can do. So they have some particular flavor to this class, but it's still very complicated. And a lot of the questions, hard questions in computable structure theory are saying, okay, here's some property that we can get in some structure. Can I get a tree that's like that? Or can I get a linear order that's like that, right? How close are they to satisfying these consequences of universality without actually being universal? So a good example of that has some questions I like is the degree spectrum of a structure. So we're looking at all the copies of the structure, and we can think, what are the Turing degrees that can compute a copy of the structure? So maybe this is a structure with no computable copy, but it has copies that are computable from various Turing degrees. What is that collection of Turing degrees? That's the degree spectrum of the structure. And so you can ask, is every degree spectrum the degree spectrum of a tree? And so basically, if you look at all of the constructions of degree spectra, you can't pass the construction through the Borel reduction. So there's no like general reason for this to work, but you can do the same construction with a tree. Essentially, the constructions never use anything that's sort of non-tree-like about any of the structures. So this is, I think, a pretty hard problem. And then for linear orders, there's certain degree spectra that are not the degree spectra of a linear order. But here's a particular one that we don't know. So there is a structure whose degree spectrum is exactly the non-computable degrees. Is there a linear order that looks like that? So again, this is not going to transfer through any kind of Borel reduction, but it's still saying something about like, how complicated is this class? What kind of coding can you do and what kind of coding can you not do? I think there's also some interesting questions about whether there's Borel reductions that witness the Borel completeness of trees and linear orders that are a little bit nicer than the ones we gave yesterday. So last time I put up this theorem, which says that in this particular construction that we had of this tree of tuples, you cannot recover a copy of the original structure in a Borel way from a copy of the tree. So there's no Borel way to do the reverse direction. But this is a theorem just really about this one construction of the tree of tuples. Is there a different way, a smarter way of doing the Borel reduction so that you can recover the original structure from the tree? Right. So this was already like quite a hard thing to prove. This is very, very hard because now you're not even saying, right, like this was hard even though we knew what the construction was of this tree. Now we're saying do something like that, but you don't even know what the construction is. So you'd have to say really something about something that can't happen in trees, which we don't have any candidates for really. Another thing you can ask is the images of the reduction. So for this tree of tuples, the image is not a Borel set. So if I show you a tree and I say, is this the kind of tree you could get as the tree of tuples of a structure? You can't really tell me whether it is or not. On the other hand, for all the nice classes, if I give you a graph that was produced by the construction I did yesterday, you could look at it and you could, in a Borel way, say like, yes, this is the kind of graph that we produced from this construction. So this is a big difference between these kinds of universal constructions and the ones for trees and linear orders. So you can ask, well, maybe that was just because we didn't choose the best reduction. Is there some other Borel reduction you could use from graphs to trees so that the image is Borel, so that you can decide if a tree is the kind of tree that came from this construction? So maybe, I guess I tried to draw this distinction between these two types of reductions. And maybe the main idea here is that the structures that are Borel complete but not universal, these are maybe the most interesting classes of structures that you can look at in computable structure theory. Or at least they have some of maybe the least understood or some of the more interesting behaviors might be found there. All right. So the next thing I want to talk about is something that's a little bit weaker than being Borel complete. And this is something Rod talked about a little bit in his talk, which is the isomorphism problem. So if you've got a class of structures C, the isomorphism problem is going to be the set of all pairs of structures that are isomorphic. So you can think of this as sort of the computational problem of saying, given these two structures, decide if they're isomorphic or not. This is a little bit weaker than being Borel complete. It's an analytic or sigma 1,1 subset of the pairs of structures, because in general, to ask if two things are isomorphic, you have to ask if there's this function, this isomorphism, and that's a second order quantifier. And it is actually sometimes sigma 1,1 complete. In particular, it's not Borel, for example, for graphs. So for graphs, you can show that there's no Borel way to tell if two graphs are isomorphic. And this transfers over sort of the Borel reductions. So for anything that's Borel complete, this is also true, that the class of deciding whether two things are isomorphic is sigma 1,1 complete. So what's the difference here? So we have this sort of picture is what's going on, that being universal is the strongest possible thing, being Borel complete is the next, and then having the isomorphism being analytic complete is the third. But somehow these two things are motivated in a very similar way, that they're somehow about classifying things up to isomorphism. What's the difference? So when you're doing a reduction, right, when you're showing, for example, that graphs are sigma 1,1 complete, what you're doing is you're saying you're producing a pair of graphs as your reduction. When you're doing the Borel completeness, you don't know you're not like fixing the pair ahead of time. You're just saying for each structure, I'm producing a graph. And so you end up sort of having some more overlap that you don't know which graph you're comparing to ahead of time. In the isomorphism problem, you're producing maybe a different pair of graphs for each instance that you're asking about. So that's a little bit weaker. These are all strict implications. And the classical example, so we have some examples that show the first one is strict. For the second one, the classical example is abelian P groups. So it's not Borel complete, but the isomorphism problem is analytic complete. And morally speaking, the way you should think of what this is saying is that there is some kind of invariance for P groups. So these are called Elm invariants, and they're sort of ordinal many of them. They're relatively complicated, complicated enough that the isomorphism problem is still analytic complete. But there's still some kind of invariance for P groups that you can't translate to invariance for arbitrary structures. So they're invariants which are like very slightly helpful is maybe how you could think of it to tell whether things are isomorphic. There's a more recent example, which is binary splitting refining equivalence relations. So these are equivalence relations that are refining. So you have one equivalence relation, and then the equivalence classes get refined to smaller ones by another equivalence relation. And binary means that it's always splitting into two parts. So this is much more recent, I think maybe 2015, that these are intermediate in this sense. And the second one is sort of interesting in that it's an example of two things at the same time. One is it's a natural class, and the second is that it's a first order definable class. So I think this was a question of Julia Knight at some point. That the P groups, that's not a first order class. And so she asked, is there a first order example? And this is a natural first order example. All right. So now I want to talk a little bit about complexity theory and finite structures. And so I don't know if there's any people here who work mainly in complexity theory or sort of more computer science. But things work, there's some similarities, but also some differences that I'm just going to talk about briefly. So you can think of Borel reducibility as analogous to the study of the graph isomorphism problem. So what is that? It's a computational problem that, for finite graphs. So I say, given these two finite graphs, I ask you, are they isomorphic? So it really is the same as the isomorphism problem that we just talked about, but for finite structures rather than countable structures. So of course, for finite structures, we're measuring things, is this in P and NP? What kind of complexity class is it in? And there's this, for a long time, this was thought about, and I guess this is less than 10 years ago, it was shown to be solvable in quasi-polynomial time. So this is not quite polynomial time, but it's presumably, if P is not NP and the world is kind of how people expect it to be, this is a lot faster than an NP complete problem. So this is a natural candidate for a problem that's intermediate between P and NP. But like in complexity theory, you always have to say, if certain assumptions are true, then this might be true. So we're going to say that some problem is GI complete for graph isomorphism complete if graph isomorphism is polynomial time reducible to that problem, right? So this is some kind of completeness notion that maybe is between being polynomial and being NP complete. And so just like for the infinite structures, this translation into graphs, I guess for whatever reason, historically in computer science, they always talk about graph isomorphism, but it's really isomorphism of any kind of structure presented to you by the same kind of translation of any structure into graphs. So there's this whole sort of industry of studying certain subclasses of graphs and saying, for this subclass, is it rich enough that the graph isomorphism problem for just this particular kind of graphs, is that still graph isomorphism complete? So for example, if I take bipartite graphs, is it just as hard to tell if two bipartite graphs are isomorphic as it is to tell if two arbitrary graphs are isomorphic? Or you can do this for chordal graphs or any kind of graph you feel like. So there's something, this is not an area I know too much about, but there's something I've noticed in reading about it a little bit, which is that the reductions they use are always like reductions that are like the universal kind of reductions. So whenever you reduce some graph into some kind of other structure, or maybe some particular kind of graph, you can always find the original graph inside the one you produce in this nice way, like the universal constructions. And that's even though, technically the graph isomorphism problem is defined analogously to the isomorphism problem, which is the weakest of these three things. Nevertheless, the reductions always seem to be the strongest version. So as far as I know, that seems to always be true. So that's something I'm kind of interested in is there any example where that's not the case? I'm going to talk about maybe why that might be the case always. But first, let's talk about bipartite graphs just as a nice little example. They are complete for graph isomorphism. So what are we going to do? We're going to use this standard kind of thing where we turn a graph into a bipartite graph. So given some graph G, I'm going to produce a bipartite graph, and it has to maintain isomorphism. So if the two graphs were isomorphic, that should be true if and only if the two bipartite graphs I build are isomorphic. So it's going to be bipartite. One part is going to be just the vertices of the original graph, but the vertices of the other part are going to be the edges of the original graph. So I'm viewing the edges of the original graph as the vertices of the graph I'm producing. And basically, so if this is my original graph, I'm putting the vertices of the original graph on one part. The other part is the edges, and then I'm just connecting an edge. So this vertex here represents this edge here. I'm connecting the edge to the two vertices that are incident upon it. So, I have this edge corresponds to this vertex. This edge here corresponds to that vertex. There's no edge from here to here. That means there's no vertex here that's connected to U and to W. So you can see that you can recover the original graph from this. So this is really this same style of this kind of universal construction we've been talking about. There's a whole bunch of graphs that the graph theorists are interested in. One particular kind is graphs defined by a forbidden subgraph or a forbidden induced subgraph. So we're going to talk about forbidden induced subgraphs and just one forbidden induced subgraph. So you have to make the distinction for subgraphs between, in the subgraph, do you maintain all the edges that were in the original graph, or are you allowed to drop edges? So an induced subgraph is a subgraph, but all of the edges of the original graph, if those vertices are included in the subgraph, then you also have to include the edge. So you can delete some of the vertices, but you can't otherwise delete any edges. And there's this theorem that says if I'm going to forbid one induced subgraph, so H is the induced subgraph, C is the class of all graphs that don't contain that, then this class is going to be complete for graph isomorphism if and only if H is not the path on 4 vertices. So essentially the place where behavior changes is whether or not you have an induced copy of this. So if you're allowed to have copies of this, then the isomorphism is going to be complete. If you're not allowed to have any copies of this, then the isomorphism is going to be in polynomial time. So in the case when it is complete, so when you're allowed to have copies of this, it is again by this sort of universal kind of construction. But let's say just a little bit about what happens in the other case. So let's think just of the class where we forbid any copies of P4, this path on 4 vertices. So this is a class of graphs called cographs. And they have this characterization. I couldn't figure out exactly like where this came from. It seemed like there were a lot of people sort of publishing things that were little small increments on each other all around the same time. But there's this sort of recursive construction of these graphs. So you can build them up basically from single vertices. So you say a single vertex, that's a cograph. And you say if I have any 2 cographs, I can take their disjoint union. And in general, any number of cographs, I can take their disjoint union, and that's still a cograph. Or I can take the complement of a cograph, and that's still a cograph. So the complement is I'm switching all the edges to non-edges and all the non-edges to edges. Another way to think of this, so I could replace this third one by saying that I'm allowed to take like a join or a complete union, where if I'm taking the join of these 2 things, for the disjoint union, I just put them in and no edges. For the join, I'm going to put all of the edges between them. So it's kind of like the complement of the disjoint union. So for example, if I want to build up a cograph, I could start with this. I could take the disjoint union of these 3 things. I could take its complement, so that would look like this. I could take the disjoint union with a single point. And then I could build some other cograph here, and I could connect all of the vertices in all the possible ways between these, and that would build a cograph. Another way to think about cographs is for a cograph, it's either going to be, and this is sort of true hereditarily, it's either going to be disjoint or its complement is going to be disjoint. So if it's disjoint, I can turn it into its connected components. If its complement is disjoint, I can take the complement and then take those connected components. So I can always sort of decompose it. In particular, you get a tree decomposition, right? So you can think at the root node, you have the full graph. And then if it divides into connected components, you can put the connected components as the children. And then those are going to be connected. So you're going to have to take the complement. Once you take the complement, it's going to be disconnected. You can think of all those connected components and so on until you get down to the single elements at the end. So every cograph, you can find this sort of tree decomposition of how to build it. And for finite trees, even labeled trees, so these are labeled essentially with whether you're taking a disjoint union or the complete union, you can decide isomorphism for labeled trees, finite labeled trees in linear time. So there's this old algorithm, which I think is essentially the only algorithm that people know in linear time. And it importantly uses counting. So essentially what it defines like an order on trees to say that certain trees are less than other trees. And there's various cases, but one case, for example, is if this tree has less vertices than that tree, then it's going to come first. So this really importantly uses the fact that the trees are finite and that you can count things. And so that means that the isomorphism problem for cographs is polynomial time, because first you find the tree decomposition of the graph, you find the tree decomposition of the other graph, and then you ask, are those the same two tree decompositions? And then you can decide that in linear time. So you've decided if they're isomorphic or not. Now, you notice that right, it's really using these trees. And for countable structures, trees are actually suddenly very, very complicated. They're Borel complete. And because of that, the countable cographs are actually Borel complete, but not universal. Essentially, they're not quite the same as trees, but they're very similar to trees. So, given a countable tree, you can essentially take that countable tree as the construction of a cograph by using it as the basis for this tree decomposition. And then you've got this reduction because trees are Borel complete. The countable cographs are going to be Borel complete. On the other hand, it's not going to be universal. For sort of similar reasons to the tree, it's a little more complicated. You have to use a modular decomposition. You're never going to get the cyclic group of order 3 as the automorphism group of a cograph. Cographs are maybe a little more complicated than trees. Basically, they're also close to under nested unions, and that's not something that corresponds to trees. But essentially, the idea is they're strictly more complicated than trees, but only by maybe a little bit. So morally speaking, what's happening here is that when you show that trees are Borel complete, you're taking this tree of tuples, and that's really an exponential explosion of the number of vertices. So if you have n vertices that you're considering, and you want to take the tree of tuples, right? There's a lot more than polynomial in n different tuples. Your trees, you got this tree, the tree is growing exponentially. And so if you're thinking of things up to polynomial time, you can't really do these reductions that allow this exponential growth. Things are bounded in size. And so it seems like this sort of tree-like behavior somehow seems to not show up. So that's very like an intuition. But I think there's some interesting questions. Basically, is there a class of finite structures which is like trees in the sense that it's complete for graph isomorphism via this kind of Borel reduction style argument, but not via a universal type of argument? So something that somehow behaves like trees, except that, of course, it can't behave exactly like trees because of this counting thing, but somewhat similar in some way. Or is there something that's like P groups, right? So it's graph isomorphism complete, but there's not even this Borel type reduction. So somehow it depends on, so you should think of something like this. What's going on here? It's saying that if I give you two graphs, then you can build two finite structures so that the two graphs are isomorphic if and only if the two finite structures are. But that if you take like three finite structures, you might build two different structures for this pair, two different structures for this pair, and two different structures for this pair. Whereas if you're going to have this Borel type reduction, if I give you three structures, you should be building only three structures. So you have like a little less flexibility. You don't know what you're comparing it to in this Borel reduction. All right. For the end of the talk, I want to talk about torsion-free abelian groups. And going back to the beginning, one of the first examples we talked about was the rank 1 torsion-free abelian groups, or the subgroups of the rationals. In general, you can think of the rank n torsion-free abelian groups. So these are the subgroups of q to the n. They have like n independent elements. And to be properly rank n, you should not be a subgroup of q to the n minus 1. So we're going to call the class of these rank n groups torsion-free abelian groups of rank n. And there's a Borel reduction from each rank to the greater rank. And the reduction is just you take a group and you take its join with the integers, the direct sum with the integers. To to see this is a reduction, you have to see that this maintains isomorphism, and it does because there's a cancellation theorem for integers. So Kahn and Walker have this cancellation theorem that if you know that these groups are isomorphic, you can cancel out the z's from either side and get the g and h are isomorphic. So this really is a Borel reduction. Now, this is a good case for saying, like, if you're a computability theorist, why should you think about Borel reducibility and not just about the isomorphism problem? These classes can't be distinguished in terms of their isomorphism problem. No matter what rank you're choosing, it's going to be sigma 0, 3 complete. On the other hand, for Borel reducibility, these are all distinct. So, it's each of these is like it can't be reversed. This is a very hard theorem. So Thomas's paper was in JAMS, for example. Personally, I don't actually know how the argument goes. But basically, what it means is that their invariance for each of these can't be used as invariance for the next one. So they're getting strictly more complicated as the rank goes up. I want to put this question up, which is a question that appears in a paper of Turbo Ho, Julia Knight, Russell Miller. I'm going to include Philip Dittman's name on it because I know he was talking to them about some of these things. So we're going to look at fields of finite transcendence degree, same characteristic 0. You can, just like for groups, get this reduction of things to things of higher transcendence degree. And the question is just, are these strict like they were for the torsion-free abelian groups? For the reductions, in this case, it's actually a lot more complicated. And I guess this is where they were talking to Philip Dittman. So the reduction uses valuation theory and Henselian valued fields. Basically, what you do is, given the field K, you form K of X. It's got a valuation on it, given by the sort of natural valuation of degree. And you can take something called the Henselization of this. That gives you a slightly bigger field. And the point is that the valuation can be now recovered. There's only one valuation on an Henselian field. And so K is the residue field of this field you produced. You have to do actually something more complicated. Just going K to K of X doesn't actually work. You can have two different fields that have the same field when you adjoin a new indeterminate. This is something about like stably rational. It's very hard algebraic geometry to make this example. So that's an interesting question. Sorry? I don't think I think it was mostly Philip and your ideas. All right, and then for the end of the talk, we're going to talk about torsion-free abelian groups, not a finite rank of infinite rank. So in this original paper by Friedman and Stanley, sort of maybe the most important and the long-standing problem that they left open was whether torsion-free abelian groups are or aren't Borel complete. So I forget when this was. I think it was like around 2010. Rod Downey and Antonio Montalban showed that the isomorphism problem for these is analytic complete. So remember, this is a consequence of Borel completeness, but potentially like P groups, it doesn't imply Borel completeness. So you can think of this maybe as like some evidence towards it being Borel complete, but not all the way. But it's some progress. And then recently, Shala and Paolini announced that they did have a proof that torsion-free abelian groups are Borel complete. They published a proof. There were some mistakes. They were fixing the mistakes. Laskowski and Ulrich announced a different proof, going through what looked like on the surface pretty different methods, that torsion-free abelian groups really are Borel complete. So the proof is very technical. So this is just like a screenshot of a little bit of the proof, one definition from the proof. And it's one definition that I've cut out 7 to 9, and 11 keeps going. So you can see it's very, very technical. And the Laskowski-Ulrich proof is also pretty long, but it builds on other things that are also themselves relatively technical. So to end the tutorial, I'm going to try to, I'm not going to be able to give a proof of this, but I want to try to highlight some of the main ideas. What are the new things they had to introduce in order to solve this? And the structure of the proof is really, it breaks up into two parts. There is a combinatorial part where they construct a purely combinatorial structure using equivalence relations. So this is some set and certain equivalence relations on this set. And then they use that set as the generators for a group. So everything in the group is some rational times an element plus some rational times another element plus some rational times another element and so on. But they're not taking all the rational combinations. They're only taking certain rational combinations. So and which ones you take sort of is influenced by how these equivalence relations go. So it breaks up into these two parts. They're intertwined because you were building the combinatorial part in a certain way because you have to do a certain thing when you build the group, and vice versa. So what's the sort of naive thing to try to do? So you want to take a graph and you want to turn it into a torsion-free abelian group. So maybe what you want to do is, this is kind of what we've learned, is probably you want to have certain group elements that represent the vertices. So maybe you pick a group element X sub V to represent the vertex V. And then now you have all these other elements that you're going to form, right? Because you can add all these X's together and so on. So maybe you want to try to highlight which of these special things are representing vertices. And really the only thing you're ever allowed to do when building one of these groups is you're allowed to add divisibility relations. So you could say, this element 2 is going to divide that element infinitely many times, but maybe 2 is not going to divide that element infinitely many times. That distinguishes these two elements from each other. So you might say, okay, I want to add divisibility relations to this particular element X. But the problem is that if you do this, then you're going to add divisibility relations to U and to XV, and then you've also added divisibility relations to XU plus XV and all the other combinations, all of them, and it's suddenly a whole big mess. And you've added divisibility relations to all sorts of things you didn't want to. The other thing you might want to do is, if there's an edge between two things, you might want to say between U and V, you might take XU and XV and form something out of them, like adding them together. And you might say, I want to add some kind of divisibility to this. Maybe I used 2 already there. Now I'm going to make this divisible by 3 infinitely many times. But then you have this problem that you can form new things out of this that you didn't want to add divisibility relations to. So say I had just this graph on 4 vertices. S goes connected to T, connected to U, connected to V. Well, so maybe I'm adding divisibility to this, and to this to represent those 3 edges here. But then I can add them all up together, and I'm going to get the same divisibility relation on this. And this element is representing an edge that goes from here to here, and that wasn't supposed to be there. So I added these divisibility relations to certain things, and I got divisibility relations on other things where I didn't want them. So it's sort of all a big mess. It's hard to put exactly the divisibility relations that you want to put. All right. So I'm going to try to talk about how you go about solving this. So a warning, the rest of the tutorial is going to be pretty technical because we're talking about these divisibility relations, but also not technical because I'm going to wave my hands. So I think it's going to require some suspension of disbelief on your part to just go along with things and get the feeling. Okay, so now I want to try to highlight some of the main ideas. So the first main idea is that if you're taking this structure and you're trying to transform it into a torsion-free abelian group, you're not just going to have one element in the group, one generator representing each thing in A. You're going to actually have a whole bunch of them. So for each element of the original structure, you're going to have an infinite set X sub that original element, and your group is going to use all of these as a Z basis. So these are going to be generators of your group. And if you only took the Z linear combinations of these, this is what you would get. So this is you take only integer combinations of the X's. The sort of biggest group you could get generated by them is you take rational linear combinations of them. Our group is going to live somewhere in between. So it's going to have all the integer combinations, and then it's going to have certain other divisibilities, but not all of them. And we should think, the things in the same set XA, we think of them as somehow being, they should somehow be related because they correspond to the same elements of the original structure. So maybe a nice way to think of that is that there's an equivalence relation on the set X that partitions it into the different elements of the original structure. All right, so the second main idea is we're going to have a whole bunch more equivalence relations. So for each size of tuple, we're going to have an equivalence relation on those tuples. So the set X together with all of these equivalence relations, that's really going to be the combinatorial structure. And the idea is to have some kind of lifting of isomorphisms between these x's with these equivalence relations in the original structure. So if you divide it up into the xa's, you have xb and xc. So if you have an isomorphism of the original structure, that's going to move the a's and the b's and the c's. You want these corresponding sets to also move. So any isomorphism of the original structure should induce an isomorphism of these equivalence classes. But weirder things might happen inside of the equivalence classes. So for example, if you map this to this, this to this, and this to this, maybe you're going to have this element goes to this one, this element goes to this one, but this element is going to go to this one and not go back to the original one. So this is where you're taking advantage of having lots of different elements representing the same A, is that a cyclic automorphism in the original thing might not induce a cyclic automorphism on the x's. The other thing we're going to want is that the automorphism should should fix each of the equivalence classes E. So it's behaving differently. So the X, it's respecting it. So it's going to move the equivalence classes. On the E's, it wants to fix each equivalence class. So for example, here, there's this equivalence on single elements, E1. Each of these elements should all be in the same E1 equivalence class if they're going to map like that in an automorphism. So intuitively, you should think of these equivalence relations on the tuples really as saying that it's allowable to map the one tuple to the other in an automorphism, right? So the automorphism should maintain these. That's saying that any automorphism has that property. And moreover, somehow it should be allowable that if they're related, it should be possible to map the one to the other. So the E's are really going to capture the structure being coded because they're restricting the kinds of automorphisms you can do. So if in the original structure you can't map A to B, then it's going to be the case that no element here is E1 related to an element here. So that's how you're capturing the original structure is with these equivalence relations. So again, if you can't map A to B, then each element here should not be E1 related to an element here. If you can map A to B, then everything here should be related to at least something here. Because if you're going to map A to B, this is going to map to somewhere, and they have to then be E1 related. So for a lot of the rest of the talk, we're not going to worry too much about this idea of it seems counterintuitive, but because we're trying to code some structure in, but we're not going to worry too much about how to capture the structure being coded. We're just going to think that we have these E's and what are we going to do with them. So we're going to maybe just distinguish from an automorphism, right? For an equivalence relation, an automorphism just respects the equivalence relation. This is a little bit stronger that we're asking for, that we're actually fixing each of these equivalence classes. But maybe we'll call this a strong automorphism. So we need to add some divisibility relations in. So we're going to pick a bunch of primes. So these should all be distinct for every tuple of integers and every equivalence class. And there's some technical conditions to make things work out. And then we're going to define our group by adding some divisibility relations. So if we have some tuple X, so this is a bunch of different elements from the set X, the generators. And we're going to take their equivalence class E. And if we form some sum of them, so the sum of Qi, Xi, then we're going to add the divisibility relation that the corresponding P infinitely often divides this sum. So in this just the group generated by the generator, so without worrying about the divisibility, everything looks like this. And so you're sort of distinguishing for each of these tuples based on what coefficients you used and what equivalence classes the X are in. You're trying to distinguish them from each other a little bit. So maybe here's an example of how this is going to work. So one thing you want to do is you want to distinguish each of the elements in each of these sets X sub A, right? Because there's also, these are the generators. So there's also elements that are like this plus 2 of this plus 3 of this and so on. So you want to say something about, these sets are special. They can be distinguished from each other. So say we have some x, and we want to try to distinguish x from some sum of other elements with at most two other elements. Because it might look the same as some sums with one other, an element here might look the same as an element here. That's perfectly fine. But an element here shouldn't look like something from here plus something from here. So say it does look like this. And what you're going to do is you're going to take the equivalence class of those y's, and you're going to take those coefficients, and there's a divisibility relation that's showing up. So we said that this prime here is going to infinitely divide this sum, which is equal to x. So we now have an infinite divisibility of x that we got there. In particular, x can be written as a sum of things that were those kinds of things that had this divisibility relation. So you can write as a sum of linear, like a combination of things with that kind of form, where they all are in the same equivalence class as y. But the problem is that maybe this could just be true. There's no reason a priori that x can't be written in some form like this. So you need to do something special to make sure that this doesn't happen. And this is sort of the third idea, which is imagine we have a whole bunch of elements, tuples of the same size, and they're all in the same equivalence class. So I want to look at, they're all tuples, but I want to look at the individual elements that show up in those tuples. It could be that some of those elements show up in multiple tuples. So, maybe the second element of this tuple is also the third element of that tuple. But the thing you have to make sure happens is that there should be at least two of those elements that only show up once. So that's what this is saying, is there's these two elements that come from those tuples that only show up once. So they're not equal to any of the elements in any of the tuples. So basically this is saying in any set of equivalent tuples, there's two elements that only show up once in those tuples. And in particular, what this means is that in the right-hand side here, two of those z's have to only show up once. Right? Of all of the different zij's, there have to be two things that only show up once, and then there's nothing to cancel with them. And so then you're going to get a contradiction, because you have one of the generators is equal to some of the two of generators at least, or maybe more. And so this can't happen. So you should really think this is like a sort of non-cancellation kind of thing, that when you take some sum and you take a bunch of elements which somehow look very similar, they have the same divisibilities. You add them together, there might be some cancellation from things because the two sums might involve some of the same elements, but there's got to be at least two things somewhere that don't ever cancel with anything. And they kind of keep the character of what was going on, or like they let you recover the fact that you actually did some things in the first place. All right, so you can basically think the height of the combinatorics is in a kind of structure like this. So we have some structure M. You should think of M as the set of all the x's. And you have this equivalence relation X and these other ones En. So there should be infinitely many X equivalence classes that you can use as these X's. You want to have this permutation, this automorphism. So I'm doing it here like as if there's no structure. So think of this as like if I'm trying to code the totally disconnected graph. So like any automorphism of that should induce an automorphism of the equivalence classes. And we should have this thing about the equivalence relations that any set of equivalent elements, there should be two things that only show up once. So you want to build some kind of structure like this. And you might think if I want to do something like this, this is kind of, right, this is just saying there's lots of stuff. This is some kind of homogeneity. It's saying somehow that any map that I could do does actually exist. And so you might think, okay, I want to do some kind of Frege construction. But it turns out that this third condition breaks that. And so it doesn't work to do a Frege construction. And basically the problem is that you could have two tuples that both, they look the same. So in the Frege construction, you want to make it homogeneous. You want to map one to the other. And they both look reasonable right now, but they're incompatible in the sense that you can't amalgamate them in a reasonable way. So they're both individually reasonable, but not reasonably amalgamated. So this is an example of what it looks like. So maybe focus on the two tuples, there's the tuple of the A's and the tuple of B's. And the idea is that in a Frege construction, what you want to do is you want to say, this element exists around the A's, so I should make something over here that looks like that, but relative to the B's. So I want to add something that looks like this, but over here. Each of these individually is okay. So if I look at like this tuple and this tuple, I have two elements that only show up once. This only shows up once, and this only shows up once. So that satisfies that third condition. Over here, I also satisfy the third condition, because if I take like this tuple, and this tuple, I still have two elements that only show up once. So currently, this satisfies that third condition. But then when I want to do this Frézé-style amalgamation, I'm going to amalgamate this over here. I'm going to get this element here. And now I'm going to violate the third condition. Because if I take this tuple, this tuple, this tuple, this tuple, and this tuple, everything shows up exactly twice. I don't have any elements that show up only one time. So these two, both reasonable individually looking things, can't amalgamate to something that satisfies what we want. So you could think basically that for a tuple, there's like these potential problems. So this is some potential problem. It's not currently a problem, but it could be a problem. This has a potential problem, not currently a problem, but could become a problem. And we should really think that these two elements shouldn't be amalgamated because they have incompatible potential problems. So we should only amalgamate things that have exactly the same potential problems. So what you could do is you could think of each tuple having a larger set, like going to give it as its closure, which contains all of its potential problems. And you can think that sort of, we're going to use the closure to decide if two tuples are similar enough to amalgamate. So you can think of the closure as kind of like guarding A from its problems. All the problems are contained within the closure. And we're only going to homogenize two tuples when their closures look the same as each other. So, when would we homogenize these? Well, their closures, this guy is going to be in the closure of these things. So to homogenize this, amalgamate this and this, we're going to have to know that the closure here looks the same. So it's going to look like that. And those, I guess they're already homogenized, right? This tuple that looks like this already exists over here. So to build something like this, you have to add a few more properties. But once you do this, so it's a shorter list of properties than the original one that I took the screenshot, right? It's only 5 properties and not 12, and they don't have subproperties. But this, I think, contains like the heart of the combinatorics. So these are all the sort of reasonable ones, just saying that the kinds of things you want to have happen. This is what we want at the end, that any set of equivalent tuples has 2 distinct things. And you have to add in this extra condition to carry along, which basically says that, if you think of this one as saying that any string of things in the same equivalence class has 2 ends, this is kind of saying that there's like one end that comes out of the closure in some sense. And once you do this, you can do a Frézé-style amalgamation. So it's not technically a Frézé limit. There's all these sort of generalized kinds of Frézé limits. Technically, it's weakly homogeneous, and its H has what's called the cofinal amalgamation property. So this combinatorial structure I talked to you about doesn't really include the structure to be encoded in the group at all. To do that, you really have to include some more stuff about how the equivalence relations are going to behave to code the group. And the fourth main idea maybe is that there's a really natural way to do that, which is instead of reducing graphs to groups, we should reduce structures which have 2 equivalence relations. And it turns out that this is Borel complete. So you've already got equivalence relations reducing, you're turning them into equivalence relations, and it turns out to be a little more natural to incorporate into the construction. So of course, lots more details to check, but maybe that's a general idea of the argument that if you want to go read it yourself, you can keep that in mind and look for the hints of where those kinds of things are happening and the huge monstrosity that it is. All right, so that ends the tutorial. So essentially, maybe the takeaway, if you're going to remember one thing, it's that these structures that are trees and linear orders that are Borel complete but not universal, or groups, torsion-free abelian groups, these are some of the most interesting classes of structures in computable structure theory. And there's a lot of like really interesting behavior that's going along there. All right, thank you.
Thank you, Matthew. Let's do the mic extension. And in the meantime, while they're untangling, who has the first question?
Just to be clear, this last proof that you were describing.
For accessibility.
So just to be clear, this last proof you were describing, that's your proof, or was it the proof of these other people you mentioned?
So it's like my attempt to understand their proof.
Yeah.
So it really follows like the combinatorial ideas are from their proof, but packaged in a different way. The Shala column.
Yeah, you mentioned two others. So like the first one, the faulty proof by Shah and somebody else, is that also written up, or do they?
So the Shala one is the one that these ideas are following. So it's so they had like some mistakes, but the mistakes are fixed now.
And it has been written up.
Yeah, and at least accepted, I think, if not published.
And what about you?
So I'm in the process of trying to write it up, but I haven't finished that yet. So.
Folks, we do have time for a couple more, so no shyness.
Oh, do you know if Friedman and Stanley ever tried to do anything about what are sometimes called binary reductions? Right, so I mean, you were saying you want to know whether A and B from one class are isomorphic, and you do it by computing a C and a D from another class and also if they're isomorphic. But instead of doing this for every single structure from the first class, sometimes there's a uniform way to do it. Just given the pair AB, computer pair CB, which is isomorphic in the second class, if and only if AB were isomorphic.
So you're saying basically reducing the isomorphism problem from one to the S?
Yeah, so thinking of the isomorphism problem as a set of pairs, and just doing a reduction, like an N reduction on those.
I guess I'm not seeing how that's different from like showing the isomorphism problem as sigma 1,1 complete, or
Well,
or are you saying for things that aren't where it's not
yeah,
complete? Like,
yeah.
Yeah, I guess I mean somehow that should always, by sort of like wage things, it should always be some natural class, I guess. And should really correspond to like Scott ranks of things somehow. Probably, but I don't know if they've ever thought about that.
Okay. Next, let's move it.
So you describe kind of like this dichotomy of classes, which are kind of not, which are Borel complete, but not universal, which I guess means like Borel types per or something. So can you think of any kind of a type of reduction like in between those two? Like they could like give like any clue of like what's going on, like why it doesn't work?
Sorry, you were saying which intermediate classes were you talking about?
So like now you have like Borel complete classes,
Yeah.
which are not universal. So by like this not universality in the sense of bioduplication,
Yeah.
so which is really like very strong. But like you could have like things in between, right? Like reductions in between. Do you know if there's any kind of natural form of reduction that exists in between, or like doesn't make sense to come up with something?
Yeah, I mean you could ask for things like a non-functorial inverse. But I don't know if there's any examples where that happens. So that's in some sense what those couple questions at the beginning were asking is like, is there for the trees and linear orders, is there some slightly better intermediate kind of thing? You know, you're not going to get the full universality kind of construction, but is there one that has like a little better kind of inverses? Yeah, so I guess the answer is I don't know if there's anything, but that's an interesting question.